This question is titled, why is a list slower than a collections.deque? And anytime we ask a question of why is something slower than something else, well, we either mean this operationally. Somebody went off and they measured this, and we have to go and look for, oh, you used this micro optimization that's no longer valid or whatnot, which between you and me isn't often an absolute waste of time, because those micro optimizations, they change as the various versions of Python change. And if your micro optimization is interacting with a third-party library, who knows how that might change as the third-party library itself changes. And so I always feel like those analyses are sometimes extraordinarily limited. In fact, I would say that oftentimes the just measure two things and see which is faster, unless you see a really significant change, or you can build a causative model that says it must be the case that one is faster than the other, I often think that these things can be very difficult to really put into long-term use. Here, in this question, we're referring to operations that we can perform on a list and a deque. And we're not referring to operations like appending to this structure, because we'll see that appending to a list or appending to a deque seems to be about the same amount of time. So that's not the operation that we're looking at. Well, what about an operation that adds an element to this structure or removes an element to the structure, like popping from this? Okay, we'll see again for the list and the deque, largely the same amount of time for popping from these, and it seems to be largely constant time, or at least there doesn't seem to be a relationship evidenced in these results between the size of the data and the amount of time that it takes. If we look, however, at inserting an element at the beginning of this structure, we will see a very clear relationship. And again, we're not using these timings in order to fit a curve or to fit a model. We're looking at these to just very broadly corroborate an intuition that we might have. And this intuition is that inserting an element into a list at the very beginning may be more costly than inserting an element into a deque at the beginning. And we might think that there may be a structural reason behind this. In fact, there is. If we think about how a list is implemented, it is probably, at the CPython level, some block of contiguous memory for the references of the objects that are contained within. And we know this because, for example, a list can be heterogeneous, and since it's heterogeneous, it would be very difficult for us to get fast lookup by index into the structure if we didn't know exactly how to find those elements by just taking some memory offset and adding some third element plus 3, that's where the element is. So we have that intuition. And we can think that appending is actually pretty straightforward. A fixed block of memory with a bunch of empty stuff at the end, we just fill in the next block of memory. This is a pretty fast operation. But inserting, what we might call in this case appending to the left-hand side, well, it means we have to shift every element over. And if we have this fixed block of memory, what we can think is as the structure gets larger and larger and larger, there's more elements that we have to shift over, and that's probably why we happen to see that timing behavior that corresponded to the size of the structure. And here you can see a very simplistic implementation of append left, and pop on a list-like structure. It doesn't handle things like resizing, and one of the things that you might need to do is figure out how do they make sure that as the structure is resized, they don't lose the behavior that we have analyzed, namely that appending is a very fast operation, a constant time operation. How do they not lose that? And it requires a little bit of tricks. For example, if you look at the second order derivative of how these structures grow, you'll see that that's constant. So that means that it's doing some sort of pre-allocation, some sort of doubling style pre-allocation. But I want to show you broadly how the collections.deque is implemented. In the collections.deque, you have the same block of storage, but instead of having just the size of the structure that you determine where to put an element, you have two indicators, a head and a tail, for where you're going to put elements. And when you append, you just move that tail index. When you append to the left, you just move that head index, and you allow them to even wrap around. And so here you can see a very simplistic implementation, minus a lot of important characteristics, like what happens if this thing overflows. But you can see a fixed size collections.deque that allows you to append or append to the left-hand side to insert with the same speed. Now, before we move on, there's one important thing that I want to share with you. When we look at these analyses, we're often talking in the abstract, we're talking in the asymptote, we're talking about what happens when the data set gets very large, we're talking in a very theoretical mindset. And it is not the case that Big O is not without its own controversies, not only because it's a very loose bound on the function itself, but also there are people who say that we shouldn't even teach Big O to undergrads in their CS education, in part because in practice, what actually makes something fast or slow is often very determined by things like memory, cache locality, whether an operation is actually linear time or not, all of these concrete details. Big O ignores constant factors, and that's not really something that you can do if you actually need to, on a stopwatch, time how something is going to behave. However, my counterpoint for why Big O and asymptotic analysis is valuable is, one, most college education up to maybe like halfway through your sophomore year is babysitting anyway, so what's the harm in teaching people Big O? And two, part of this is an exercise to get some intuition on why some code may be faster or slower, and necessarily to get some intuition that can give you operational guidance on what steps you might take to make that code faster. And you can think a little bit, in this example, you can see just some hints of we were missing some structure, we were missing some information in this data structure in order to be able to do the operation quickly. And the introduction of just a little bit of additional information, namely where the head and the tail of this structure are, allowed us to perform this operation very quickly. It is often the case that the choice of data structure is really just about how do we encode the missing information to take something that otherwise would need to recompute something. And if you think about it, if you're constantly recomputing something, that's at least one level of loop. And if you nest that with another loop, that's quadratic. That's what we want to avoid. Well, how can we use that in order to figure out where we can apply these optimizations? Where can we introduce new structure that allows us to devolve, say, an n-squared approach down to a constant time approach, or maybe just a linear approach? That's the perspective I want to take, and we'll see this in some of our other examples.